Hello, hello, hello. Hello, hello, hello.
Welcome. This is the first part of a multi-part series about programming in systems. This first part is about integer arithmetic.
Hello, hello, hello.
The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. Welcome. This is the first part of a multi-part series about application domain programming in systems. MIPS was a response to the growing complexity or cost of what are now known as CISC, or complex.
Hello, hello, hello.
The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. Welcome. This is the first part of a multi-part series about application domain programming in systems. MIPS was a response to the growing complexity or cost of what are now known as CISC, or complex.
Hello, hello, hello.
The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. And the resulting processor based on MIPS is an instruction set architecture. Computers may have different kinds of instruction sets. For example, your typical... The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. And the resulting processor based on MIPS is an instruction set architecture. Computers may have different kinds of instruction sets. For example, your typical... The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. And the resulting processor based on MIPS is an instruction set architecture. Computers may have different kinds of instruction sets. For example, your typical... The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. And the resulting processor based on MIPS is an instruction set architecture. Computers may have different kinds of instruction sets. For example, your typical... The assembly language program will be using the MIPS Instruction Set. MIPS is a reduced instruction set computer writ. Instructions of the computer tell the processor what to do. Instructions are composed of an operation, specified by an opcode, and a number of operands, which the operation uses. Classes of operations include arithmetic, logic, branch instructions, jump instructions, and load store instructions, and a few others. Operands typically include registers and hard-coded constant value numbers, or immediates. Registers are the local storage within a processor. The word size is the number of bits in an instruction, and often the general purpose registers are matched with the word size of the instruction set. A processor includes a register file, which is a set of general purpose registers programs use to manipulate data. In MIPS 32, there are 32 general purpose registers numbered $0 through $31. These registers are indexed by the numbers 0 through 31 within the instruction. $0 is a special register that's hardwired to always give the value of 0. Other registers have mnemonic values associated with them that are used to help when writing assembly-level programs in order to adhere to the correct behavior expected by programs that have to interact with each other. These mnemonics will be important later, but aren't too important right now. So let us begin with addition. In a high-level language such as C, we write addition like this: A equals B plus C. In assembly language, addition looks something like add A, B, C. Or, for a subtraction operation, such as D equals E minus F, we'll say sub D, E, F. Now, different assembly languages will have different orders of operands. In MIPS, the destination operand usually occurs first in the list of operands. So the destination operand here of A and D appear first before the order of operands is important. Now we can't actually use these variables A, B, C, D, E, F directly. Instead,
Hello. Mic test 1, 2, 3. 1, 2, 3.
we need to use register values. So for example, we might consider allocating registers to, allocating variables to registers. So the A variable might be allocated to the $1, B to $2, C to $3. One of the jobs of the compiler is to allocate variables to registers when generating the machine instructions from a high-level language. So here we see an example of an expression written in a high-level language that's rather complicated. Let's assume that the registers have been allocated for the variables F, G, H, I, and J as $2, $4, $5. In a high-level language, the expression F equals G plus H minus I plus J will get translated to MIPS assembly as follows. So we can rewrite the complicated expression in terms of the registers that are allocated to the variables. And we'll have to honor the order of operations when we generate the assembly. So the order of operations tells us to do the expressions that are first within the parentheses and then to do the subtraction. So the first operation is to add G plus H. The two registers for G and H are $4 and $5. So the MIPS assembly will do add $8, which will be the destination of the add operation, $4, $5. 4 and 5 are the source operands of the variables for G and H. $8 is a register that hasn't been allocated to any variables. It is a temporary storage location for the intermediate result generated for addition of G and H. The next sub-expression to calculate is I plus J. This is $6 plus $7, so the MIPS assembly instruction is add $9, $6, $7. Here again, $9 is a temporary register that's allocated to store the intermediate. Now that we have the two expressions, sub-expressions G plus H and I plus J calculated, we can do the subtraction. Subtraction is sub $2, that'll be the result, $8, $9. So that $8 minus $9 will get stored into $2. In the end, $2 associated with the variable f will contain the result of the expression as expected. We can also look at how this would be with the register mnemonics associated with those variables instead of the numbers. Here the variables allocated are $V0, which is used for return values from functions, $A0, $A1, $A2, and $A3, which are arguments for procedures or arguments for functions. And those temporary registers that we allocated are in fact $T0 and $T1, which do stand for temporary. We can also do arithmetic with constant values known as immediate operands, so the encoding of a number directly into an instruction. Here are two examples that are adding the value of 8 or subtracting the value of 4. Both add I for add immediate. Note that add immediate of a negative number is the subtraction of an immediate. Since we can encode the subtraction of an immediate using a negative operand for the immediate value, we don't need to have a sub-I instruction. Add-I operations can be used to add and subtract constant numbers as shown here. They can also be used to initialize registers to constant values, or they can be used to copy register values. Let's see some examples of these three uses of add-I. So assuming that the variables j and k are allocated to the registers $0 and $T1, in high-level language we may have these three expressions. J equals 0, initializing the value of j to 0. K equals j plus 10, just an addition of a constant number to a variable and stored in another. And then j equals k, which is the copying of a variable or copying from one register to another. So the first expression of initialization is done with an add-I of the destination variable, destination register, $T0, with the
Hello.